another episode of SaltStack. My name is Tom Hatch, the creator of Salt, and today I want to talk to you about how salt states work under the hood. Now, it's really easy to look at salt states and say, well, I've defined them, they run, wonderful, my system is configured, and I'm good to go. But understanding what's going on behind the scenes can be very helpful. Salt states can be broken up into 4 macro units inside of its overall function. Now, we start by writing SLS files. Now, as many people are very aware, since Salt is so pluggable, these SLS files can be written using a myriad of different language techniques. We default to just defining them in YAML, but what we really have the ability to do is define them in a myriad of different languages. So we ship with Python DSL, we ship with the ability to template those YAML files any way you'd like. Now, when we sit down and think about the philosophy of configuration management, we really have 2 spectrums. We have way over on one side a spectrum where we say, we're going to create and mandate a full Turing-complete language that's going to define how this configuration management works. Now, what you get over here is a significant amount of power for configuration management. And over on the other side, you've got a situation where you say, we're going to have a pretty straightforward linear approach to config management, but it's just going to be written as simply as possible. And so on this side, you've got a lot less power, but it's really easy to use. Now, my goal with Salt was to find a middle ground. Find a way to say that the way that we define configuration management is both simple and straightforward, but doesn't skimp on power. And this is where Salt's design of pluggable renderers, as well as the dynamics of Salt's how it renders its default configuration management SLS files. You're able to define salt states using YAML, and they are read and executed in a linear fashion, making them incredibly easy to use. And numerous tests that have been done show that Salt is very, very easy to use, and most of them that we've heard about come back and say that after that initial learning curve, Salt is the easiest configuration management platform to use. But we don't skimp on the power. Since the language itself is pluggable, we've found that a sizable majority of your configuration management files don't need to be really complicated. But every now and then, you need to pull out the big guns. And so that's why we have the ability to add templating and to have Turing-complete programming language capabilities built into that render system. And that's where we come back into having full-blown DSLs, allowing you to say, hey, this one or small collection of SLS files really needs that extra power. And so that's the rendering system. The reason that works is because inside of the rendering system, all we care about is taking that information and breaking it down to a data structure. That data structure is then how Salt operates, and we get into the compilation process. Now, as soon as we render down to that data structure, we have a data structure that we refer to as high data. Now, high data is the data structure as it is human readable. Basically, high data looks like the data that you define in those YAML files. But now we have to do some work with that high data. First, we go through and we reconcile a number of statements. And so one of those statements is extend, and another is requisite ends. When we get down to the runtime, you only have requisites, the ability to say that this state relies on this other state, and what that relationship looks like. But when you're writing states, there's this concept called requisite in. So when you're writing states, you can say state A requires that state B run successfully before state A can execute. That is the most simplest form of the requisite system inside of Salt. But we also have a system called requisite in, which is incredibly useful. So remember, with a require statement, we say state A requires state B. But requisite ins allow us to say state B is required by state A, so that you can define those requisites backwards. Now this, again, can be very useful if, for instance, you have defined a number of states and then you've got some add-ons to those states. And those add-ons can easily say, hey, I only exist if I'm included, but if I'm included, make sure that you add a requisite to this other state. The beginning of the compile process is where we reconcile those sorts of things, where we are able to come back and say, the runtime only cares about one direction of requisites. Let's make sure that they're all pointing the right way now that we have the complete data set to work with. The next thing that we do inside of the compile is that we change our data set from high data to what we call low data. And so again, high data is that more human readable representation. Low data is the machine readable representation. And low data takes everything that you've defined and defines a finite list that it's gonna run in a specific order. And so now we have our evaluation order for the runtime. And that low data also has all of those requisites defined in it, so that the runtime, which comes next, can go through and iterate over that low data and give you a finite deterministic execution. Having a non-deterministic execution can make it very, very difficult to maintain and utilize your configuration management code and to deploy it. Because if it's non-deterministic and purely event-based, then what happens is that you'll deploy to some systems and it'll work, and some, and it won't necessarily work because they didn't run the same way. Salt, on the other hand, is designed to always run the same way, and it has been from the beginning. And so now we get into the runtime. This low data is a list of individual states that need to be executed. How the runtime works is it starts at the top of that list, pops something off, and evaluates. In that evaluation, it looks and says, okay, this is defined to be evaluated first. Does it have any requisites? Does this chunk of execution data require that something else is run? If it does have a requisite, then we go through the list and find that requisite, pop it off, and evaluate it. If the thing which the first one requires something else, then we keep going down until we find that first thing that needs to be run because of requisites. Now, the great thing about this system is that it allows us to have relationships, but it also allows us to have a finite order of execution when those relationships aren't defined. So when you're up here in the render phase and you're writing your states, you can define a keyword called order. That order keyword allows you to define that these states are going to show up in a specific order. Normally the order that they show up in, are compiled to, normally that order is just the order in which they are defined in the files, which in and of itself is a really easy way to do it. But it can also therefore be really easy to say that, hey, I'm going to set up a specific thing, like enabling some package repositories first. And so I'll put order 1 on the package repository. And then in the runtime, you know that that's going to be evaluated first. And if it doesn't require something else, then it's going to run first. Now, if we move forward, there's also a bit of logic there. Oftentimes, when we want something to run before everything else, if it doesn't work, then we just want to jump out of that runtime immediately. That is where the fail hard statement comes in. Fail hard allows us to say, okay, this state that I've set order 1 we can also set fail hard true. If we set fail hard true and then a state fails, we're not going to try and do anything else. Inside the runtime, it'll jump out immediately and say, nope, there's nothing more that we should be doing here. So the runtime, therefore, is highly dynamic in its ability to be both iterative and declarative, in its ability to define relationships, but still function in a deterministic and linear fashion. The effort or the goal there being to, again, give you simplicity without skimping on capability. Now, when all is said and done and we have executed this system, we get down to the return. The return information that you get from running configuration management in Salt gives you not only the information about the fact that everything ran, but it also will return a dictionary with 4 pieces of information for every execution that happened. The name of the execution, the result, which is either true, false, or none. True and false should be pretty self-explanatory, but none means I would have done something, but I didn't, because you told me not to actually make a change. The next is comment. And so there's always a comment in there that says, that is just a string that defines and says, hey, this is basically what happened, and then changes. Changes is a dictionary which defines in finite detail exactly what was changed. The benefit of that changes dictionary is that it allows us to take a solid look at what changed and say, I know that on System X, when I ran Salt, I updated this package from version X to version Y. I know that this package was installed, and when it was installed, it was version X. When I updated this file, I can go back and look at my return data and know exactly what the diff was. Now, that's Salt States under the hood. Hopefully that answers some of your questions, and that's really all I could cover in such a short amount of time. I've already gone a little over. But thanks for watching, and if you want us to talk more in depth about specific parts of Salt States, please let us know and we'd be more than happy to. Until next time.